Good morning, everyone. I'd like to welcome you to our third installment of data warehousing. As far as I recall, there were a lot more people, so it looks like when I was gone, we shrinked a little bit. So Professor Balke will not be joining us today, so it will be basically me with you guys. And basically, last lecture, what we talked about was the architecture. So we already started going deeper into data warehousing, and we talked about different types of architecture, 3T's architectures. We talked about vertical or horizontal, thin and thick clients. And furthermore, towards the end of the lecture, we already started talking about data modeling. And we started talking about the conceptual modeling, which is the first step in modeling. It's rather abstract. You usually use it to work, to give a view for the people who are in the business. So it's a summary level. And since we're talking about data warehousing, unlike databases, you're going to hear us often, times and again, say that we're working in a multi-dimensional paradigm. And because we're working in a multi-dimensional paradigm, we'll always want to shift from what we used to do in the database, from this 2D dimension, to go to the multi-dimensional setup. And as you've seen last time, what we did is basically was a transition from the classical ER diagram and UML that we used to do. And you saw already how we shifted that so that it serves our purposes in the new multi-dimensional setup. Today, as a normal continuation, we continue with the data modeling. And since we've already talked about the conceptual modeling, then comes next the logical modeling. And in the logical modeling, we're going to start to talk about how we can actually project the data, how to structure it, and how to look at it. And there are basically two central objects that we will be talking about, which is cubes, the data cubes, and the dimensions. Dimensions, you've already heard about it last time, different granularities for the dimensions. We're going to take a deeper look into that. And we're going to talk about the different hierarchies, or as another synonym, granularities that a dimension can have. And in the second part of the lecture, we'll go into the physical modeling. That has everything to do with how the data is actually stored in your backend, how to efficiently store this huge amount of data so that when you get these complicated analytical queries, you need to be able to get the data quickly. And in order to do that, you have to be clever. You have to store it in a way that serves most of the queries that are coming. And basically, there are different types of modeling to choose from. We're going to talk into details about two of them, multi-dimensional modeling and relational modeling. And we're going to look at different types of schemas that are used in data warehouse, very popular, like star or snowflake. And this will basically be the physical modeling. So, starting off with the logical modeling. And like I said, this is the basic transition from the conceptual modeling. And the basic elements of the logical modeling is the so-called dimensions and cubes. Now recall in the represented by tables. And then we had relationships between tables, and this was basically how we saw the database. But this is two-dimensional. Now we're going to multi-dimensional. And even though it is rather intuitive to say, well, a table is a 2D dimension, has rows and columns, if you want to go to a higher dimension, basically that will be projected into a cube. And this cube depends on how many dimensions you have. It could be 3D, 4D, up until ND. And even though it's rather intuitive to say that, go from a table to a representation, it took them some time in order to figure out that, okay, going to a cube might be a good representation form. And the cube basically holds all the data in your data warehouse. You organize the data in a way that makes it possible for you to project and see the data properly in the cube. And the values are basically all the aggregates that you compute for the data warehouse that will serve your query are basically then stored in the cube. And then you have the dimensions, which are basically offer you some kind of a metadata to these entities that you have. So the cubes represent the central object that I am interested in the data warehouse. This could be the sales, this could be a product, this could be the customer, whatever it is my company is interested in analyzing. And you might not only have one cube in the data warehouse, but you can have several cubes. And each cube would serve the particular query that it should address. So if I'm asking questions about how many products I sold in the region of Lower Saxony, then probably you're going to go maybe in the sales cube of the company. If you're asking about the manufacturing process of a certain product, maybe go to the product cube. So depending on the query that you're getting, you go to the cube that has been designed to answer this particular query. So you can have multiple cubes, and each cube serves a certain analytical purpose that you've already identified in your requirement analysis, that you've already identified in the conceptual modeling. Once you have these two central objects in the data warehouse, you can start doing the basic typical operations that we've seen already also in databases, and this is where what we actually want to do in the end. We want to be able to manipulate the data in the cubes in the data warehouse. And you can do everything from selections, so you select a certain part of the cube, projections where you look at only some measures in the data warehouse, like what we did in the database where we projected only some attributes. Here we would be looking at only some aggregates. You could also do join operations and so on and so forth. So there's a lot of operations that we will be talking about. The third point we'll be handling in the logical modeling is supporting change in the logical model. So far in the lectures we have been telling you data warehouses are rather static, in the sense that once you pull the data from the operational system and you put it in the staging area and you do the ETL process, you do all the aggregates, you manipulate the data and make it ready. Once you put it in the data warehouse, it's supposed to stay like that. Often you'll be doing a lot of reads, but very seldomly you'll be doing any updates, because this is not really the purpose of the data warehouse. We want to see the evolution of data, how something evolves into something else. So going into the data warehouse and changing some of the data, that doesn't really comply with the data integrity that we typically want in the data warehouse. So you want to keep the data warehouse for reading. Fine, granted. Nevertheless, sometimes, and not only sometimes, but often, you need to change in the data warehouse. Not in the data itself, but rather in the structure of the data warehouse. So for instance, your company has a new operation, or there is a merge. So Microsoft bought Nokia, for instance, and now they want to add all the data from Nokia products into their data warehouse, or Facebook buying WhatsApp. That's a whole new dimension of data that they want, and they will probably want to connect it to all the user profiles that they have. So some major changes in the data warehouse, you have to be able to incorporate these changes and not start from scratch and rebuild everything again, but rather tweak a little bit in the logical model so that you can reflect that in the structure of the data warehouse and just put the data in. So these are the 3 points that we'll talk into details about in the logical model. And now, starting from the very beginning, we've already done the conceptual model, and now we want to start the logical model. And what are the goals that we want to do? Well, basically in the conceptual model, we already identified some facts and dimensions, and here we want to refine them. And the facts are basically the cubes. They are the central entities. They are the primary citizens, we might call them in the data warehouse. They are our focal point, what we want to focus about. So for instance, here in my company, I'm interested in the sales, in the purchase, in the price, and in the inventory. And these constitute the cubes, or the central entities that are in my data warehouse. And for each of these facts, you have to be able to assess them. And here comes the term measures. So for every fact, you might have one measure or more. So here, coincidentally, all the facts have only one measure to assess the fact, but you might have more than one measure. Depends on your needs, basically. So for instance, here for the sales cube, you can assess the sales of your company by computing the turnover, which is basically an aggregate that you compute. And as you can see, on one side, you have here the facts, or the cubes. On the other hand, you have over here the dimensions. And the dimensions, like I said before, they're metadata. They give you an extra dimension for each of the cubes here. So they give you more information at different levels. And for instance, here we have the time dimension or the product dimension. And here's something like a location dimension. And the dimension, it's not only at one level, but rather you can see that there is some kind of granularity. So you start off here from the day, which is the finest granularity in this case, and you go up higher until the month, quarter, and up to the year. And as you can see here, the year is the highest granularity. So if at one point your company has been here for a long time, for decades, and you want to see the sales over the last decade, the data is not available in the data warehouse. But since the finer granularity is there, you can always go and compute it. The problem is when you don't have the finer granularity. So if you don't have the day and you don't save it in the data warehouse from the beginning, you lose this data forever. So you always have to make sure that when you design the logical model and you establish the granularity, that you choose the granularities that you will need. Sometimes people opt to do all the finest granularities, work a little bit with the data warehouse and see which queries address which granularities. If there is a certain granularity that doesn't seem to be serving any kind of queries, or queries that are very seldom, they don't come often, then they choose to drop this granularity, and then if the query comes just rarely, you can then choose to compute it on the fly, on the run. So it is a design decision. Right. So basically, the dimensions are entities that you choose in the data model, and they serve a certain analysis purpose. And what is interesting about the dimension is that once you define a dimension, it can be associated with multiple cubes. So you don't have to build the same dimension for different cubes because it is the same data. They hold the same data, but they can serve different cubes. So back to our example here, we have the 3 cubes, the sales, purchase, and price. And they can all be connected to the same product dimension. And the thing about the dimension is they are divided into different granularities. They have different granularities, but these granularities are not haphazard. What I want to mean is that they are hierarchically organized. So like with the time dimension, you have the day, the month. So you go from the finest granularity up to the highest granularity, which means that each article is associated with one product group and only one product group. So if you have a Galaxy S4, then it's in the 4G and product group. It cannot be in the 4G and the 3G, for instance. On the other hand, the product groups can have many articles. So the product group, the 4Gs can have the iPhone 5, the Galaxy S4, so it can have a lot of phones. And this, of course, is the same for all the higher levels. So each article is associated with one product group. Each product group is associated with one product family. Each product family is associated with product category. And these different hierarchies are often called classification levels. So every dimension, you identify for it a classification level. Also a synonym for that is granularities. And as soon as we talk about classification levels and as soon as we start dissecting this data, so you have the date for instance, from the operational data system, just one single cell holding the date. And then you say, well, I want to dissect this data so I have the day by itself, the month by itself, the year by itself, because I will often have queries that come and address only the day or the month, so how many the sales in a certain month. And instead of every time on the run going into the date cell and start to compute that, I want that already ready in my data warehouse. So I want a separate cell for the month, level for the year. This dissection of the data brings up the notion of functional dependencies. And this, if you remember, comes from the basic data normalization theory that we took in databases, which basically said that whenever you have a data model, it has to have this full functional dependency to participate in a second normal form or a third normal form. So what does that mean? It means that, so if I have the date, this means that I can know, just by having the date, I know when this product was sold, which day, which month, which year. If I have a zip code, then I know where this product was sold, which city, which region, which country, just by having this number. And this is what the functional dependency is about. It's a function. Yeah. So if you have the date, you can find out the day from it. So you have a key value that is detrimental to the value of the non-key value. So this, the function dependency is typically denoted like this, and this means B is a function of A, meaning that if I know the values of A, if I know the date, if I know the zip code, then the corresponding values of B can be deduced from these values that A gives. And functional dependencies have to work all the time, meaning that in the time dimension over here, so if I buy something in a quarter, I will always know that it has been sold in this year. If I buy something in a month, then I know for sure that it has been sold in this year. But what about the week? The week can, if you say I bought something in the fifth week of March, for instance, this might be March or it might be April. So we can extend across different months. And that doesn't work in functional dependencies because then you don't know, is it March or is it April? Same thing at the end of the year. Weeks can extend across different years, and then you would have a week that is in 2012 and 2013. And so functional dependencies don't really work with the weeks. It has to be something that is very detrimental. When you talk about a certain day, then you know that it is in this certain month and not spanning multiple months. And that's why when we talk about the time dimension, it's a very popular example for that. The weeks are probably put in a different path. Of course, this can happen also in other dimensions, so you have to take a careful look to see whether the functional dependencies between these different classification levels that you have, whether it holds all the time, because it has to hold for all the levels, or it breaks, and when it breaks, then it doesn't work. Once you identify the granularities that you have for the dimensions, so you've stated, okay, I've seen now, according to my business processes, I need as the finest granularity the day, the month, year, blah, blah, blah. Of course, the day might be very coarse granularity. You need to go down to minutes, or hour might be even bigger. So once you've identified the granularity and you started identifying these classification levels, these hierarchies, you have to say somewhere that these are my dimensions and these are the levels that I have. so that when the query comes, it knows exactly where, which hierarchy, which classification level to address. And this is basically documented in so-called classification schema. So in the classification schema, it holds a list of all of your dimensions and all the classification levels that you have. So if you have a dimension D, we say it is a semi-ordered set of classification levels. It is a semi-ordered set because you might have different patterns. You might have from the day to the week, or from the day to the month, to the year, to the quarter. So for each dimension, you start off with the finest granularity, so K0, which in our example was the day for the time dimension, was the article for the product dimension, and it goes up to K dimensions. The smallest dimension, like I said, is the smallest granularity, and you always have to be careful when you choose the finest granularity, because once you choose that, everything that you've aggregated, if you had a finite granularity in the operation system and you chose not to use it, you cannot retrieve this data anymore. However, when you have the highest granularity that you chose, you can always go higher because you can always compute it, because you have the data underneath and you can aggregate that on the fly. So always be careful when choosing the granularity. A classification level, so these are basically some definitions. You've already heard me saying that term. Once you have a classification level, so this is the time dimension, and you have a hierarchy that is ordered, it's called a path. So here you have two paths in the time dimension. You have path 1 is basically you go from the day to the month to the quarter to the year. And then you have the second path, which is over here. You go from the day to the week. And again, these are defined in the classification schema. So in both paths, you start off with the smallest dimension. The smallest granularity is the day. And the highest granularity in the first path is the week. While in the second path, the biggest granularity that you have is the year. So, as defined by the classification schema, you start off from the smallest granularity, you go up to the highest granularity, and this basically makes the path. Now, there's a nice way to represent these classification hierarchies, and this can be done through a balance tree. So when you have different paths, you want to be able to understand quickly how your classification levels are, you can represent this by a balance tree. And the balance tree basically holds all the dimensions, all the different granularities and the dimensions that you've already identified, plus a node, which is all, which is the aggregation of everything that you have. And the edges then between all of these different granularities within the tree are basically with respect to the functional dependencies that you've already established in the hierarchy when you talked about it. So an example here, for instance, if we look at the product dimension, we had 4 granularities. We had the article over here, we had the product group, product family, and then the product category. And as you can see, on top of all of these different granularities that you've already established, you have here an aggregate, which is basically all the products that you've sold. So on the article level, you can have queries like how many video recorder, how many TS56 video recorder did I sell in a certain month or in a certain year. In the product group, you can do analytical queries to find out which is the most popular product group that seems to be likable for your customers. When you go up to the product family, again, you can direct queries that only handle the product family, and up to the highest level. You can answer high queries that managers would typically be interested in, like, how many products overall did I sell in the past year, regardless of whether it's electronics or clothes or whatever. And this is where the strength of the data warehouse comes from, is that you build all of these different aggregates so that when the query comes, you direct the query to the right aggregate that has been already pre-computed in the ETL process and has been stored in the data warehouse. So basically, you have all the different dimensions over here, and then you have the top-level aggregate on top, which basically serves all the products or all the time company or different locations of your stores or branches. It's the topmost level, which gives you a summary. Right. So we've already talked about the dimensions. And the dimensions, as you've seen, we're connected to different cubes, which are the central objects in our data warehouse. And you've seen that the dimension can serve different cubes. The same dimension can serve different cubes. And the cubes, we've already, in the conceptual model, we had an idea already of which entities we wanted to project or we wanted to keep track of in the data warehouse. And these were the sales, these were the prices, so in the earlier example that we mentioned. And it is basically the basic unit of the multidimensional paradigm. And like I said, the transition from the table to the cube seems rather intuitive when you want to go into multi-dimension. Now, in the table, typically, what you had is you had a column with some attributes here, and then the primary key, and then in each cell you had some values. And that was typically only one value. Now, in the cubes, usually you define a cube, and then you start also saying, for the sales cube, I'm going to assess that cube by the turnover. And this is a measure that gives you an idea of the sales. It gives you an intuition how the sales are doing in your company. But you might have different measures for that. So you might have the revenue, which is the total net price. You might have something, different measures. So you might look at the taxes, for instance. So you might have different measures that assess the same fact. And in that sense, when you have a cube now, every cell in the cube is not only a single cell, but it might be a small cuboid which holds all the different measures for that particular sale on the different dimensions. So if you have, let's say, 3 dimensions, you have the time dimension over here, you have the product dimension over here, and then the third one could be the location. Then basically you might have then in the small cell, you look at different measures, so not only one measure, it could be more than one measure. Then you start looking at the sale for a certain product, depending where you are in the cube. And since you have a lot of different dimensions, then for that certain product, it might be how many sales for this certain product on a certain day, or a certain month, or in the entire year, or in 2 months, or in a quarter. And according to the granularity of the time, you start shifting, you start moving in until you find that certain cell that holds these values. And of course, it's not only a single cell, it's a cube, because now you have a lot of different dimensionalities that you need to look in. So you might choose one granularity on the time for all the products on a certain day, what were the sales. Or you might want to look at a certain month for a certain article, but over all the different branches that you have, for instance, in Germany. Or you might want to zoom in on a certain part in Germany. And this way, the cells themselves are also small cubes that holds different values according to the different dimensions that you have. So basically, the cell then holds raw data and pre-aggregated forms. So you're holding the data that you've already gotten from the operation system, from the ETL process. And you'll see in the next slide is that you have the basic data that you got, and then because we're working in data warehousing, we always want to do these pre-aggregates. In the cube itself, you're going to start computing these pre-aggregates, and this can be easily done once you have this cube structure, which is the reason why people opted for a cube. And then you start to do these aggregations. But at the very beginning, you start off with the raw data, which is basically the center of the cube, and then around the cube, you start building these aggregates. So the cube, when you start building it, it is basically a Cartesian product of the granularities that you have, the different dimensions that you have, and you would typically use the basic granularity. So you start off with the day, which was the smallest granularity in the time dimension. You start off with the article, which was the smallest granularity in the product. And then, because when you have the finest granularity, you can start building up the aggregates for the bigger ones. You start off the cube with the finest granularity, and that is why it's then we call it in the pre-aggregated form. So it's a Cartesian product between these granularities of the different dimensions that you've identified, multiplied by the different measures that you've already established for that certain fact, for that cube, for the sales cube, for the price cube. So for instance here, for the sales cube, you have 4 dimensions. And as you can see here, we're using the finest granularity. So we're talking about the article for the product dimension, we're talking about the day for the time dimension, store for the location, and client for the customer dimension. And we have only here one measure for simplicity's sake. So without lots of generality, you can have a lot of different measures that serves the same cube. So this is the example that I want to show you. Here it's, instead of, we've been talking about 4 dimensions, but for simplicity's sake, so that you can start to imagine with me how the cube looks like and why it's rather useful, we'll stick to 3 dimension. However, everything applies to the 3 dimensions. Everything that applies to the 3 dimensions will apply to higher dimensions. But this is just for you to be able to visualize with me now. And you already see that it's a little bit tricky, and you have to have a little bit of imagination here with me. So basically, you start off here with the green part here. This is your raw data. This is everything on the finest granularity, and this is so-called the basic cube. Now you want to build on top of that all the different aggregates. So when you get the query, you go into the aggregate that you want, and you directly serve that query. So first off, we have over here the city dimension. So this is the location dimension. We have the product dimension, starting with the item. And then we have the year dimension over here, which basically goes something like this, which is the year dimension. And basically here, in this part, would be the sales of a certain item in a certain city in a certain year. And if you go up here, it's always in a certain city. And at the very top here, an item in a certain year in all of the cities. And this is the aggregated form of the city. Same thing if you go over here on this side, on the item dimension. So this cell would be probably something like in a certain city, in a certain year, what were the sales of all of the items that I'm selling. Same thing goes also for the year, but it will be at the back of the cube. And you can start building these aggregates. So I've shown you now aggregating only also build aggregates for more than one dimension. So for instance, if we want to aggregate in terms of the items, so I want to find out all the items that were sold for a certain city and certain year. So these would basically be this part over here, this part over here, and then there will be another part in the back here, but I can't really move the cube and turn it around. But it will basically be these 3 slices. if you want to aggregate everything according to the items and according to the city. So you want to find out all this, the sales of all the items in all the cities that you have, but in a certain year. Then you start looking at this part over here. So the year dimension was like here. This part over here. So these three slices. So everything is aggregated by the product dimension here, and everything is aggregated by the city dimension here, and you get here the individual years. And for that node that we had in the balance tree, which was the all, you can basically then find it in that small cell over here at the very top of the cube, which is typically referred to as the apex. And this is the single number that summarizes your business, as sometimes that might be sensible. So here would be all the sales that you had for all the items and all the cities and all the years. Everything that you've sold ever since you started your company or ever since you've held the data in the data warehouse, that would be basically here. That would be the aggregate of all of these different dimensions for that specific measure. And as you can see, having this cuboid structure helps you in visualizing how these aggregates are built. So you start off with this green cube over here, which is the raw data that you have over here, and then you start building all of these aggregates on top of the cube. And whenever you have this cube model, what you're assuming is that you're going to be building all of the different aggregates for all the data that you have. Of course, you might not need all of these aggregates, but this is the underlying assumption here when you're using the cube. You might opt to not calculate all of these aggregates, but you have the facility to do that, and rather easily. As you've seen when you want to explain to someone something like a cube, it's a little bit hard to visualize all of these different cells. So you have to look at the cube, have a little bit of imagination, and look at the different cells and start to see, okay, here at this part I'm aggregating by the city, and then I'm looking at a certain year and a certain product. But typically, if you want to visualize this cube in a rather easy way, because you've already seen we were talking about 3 dimensions. We had only 3 dimensions. There are the product, the customer, and I think the city. But you would typically have more dimensions than that. And to be able to visualize that, we typically use a lattice of cuboid. And it's like also a tree structure, and it then gives you a view of where the different aggregates are in the cube. And so over here, which was the green cube in the last slide, this is where your raw data is. So this is where the data for each city, for each item, for each year is stored. And as you go up in the cube, you start building these aggregates that you have. So over here is an aggregate. You're aggregating everything according to the year. So in all of the years, you can start look at a certain city or at a certain item. At this far end of the cuboid, you can aggregate here everything according to the city. So in all of the cities, how did a certain item do in a certain year in terms of my turnover, in terms of my sales? If you go up here, then you're aggregating everything according to the 3rd dimension, which is the item. So for all of the items, I want to find out for a particular city, for a particular year, what were the sales. If you go up on the higher level, then you start getting this one-dimensional cuboid, where you're only focusing on one single dimension, either the year or the item or the city. And what's interesting here is as you go up and you start building these aggregates, you don't have to build the aggregate from different paths. Meaning, in that first level, in the 2D cuboids, you had aggregates for the year. So you aggregated the year, and then and now if you want to build a city aggregate on top of here, you can either compute that from these cells over here, or from the values over here. Both of them hold the values for the cities. However, you cannot get the data from here, because over here you've already aggregated all the values for the cities. They are already all the sales for all of the cities. You don't have the data anymore of the sales that you did in France or in Germany. They are for all the different countries or all the different cities that you have. So when you're computing the aggregates, you don't have to compute them from the different paths. You can only compute them from one path. They're the same data. They have just been projected in different manner or with different dimensions. And at the very top over here, you have this apex cuboid, which is basically the summary of everything. So all of the sales that you did in all of the cities and all of the years and over all of your products. So you start with the base cuboid down here, which is the raw pre-aggregated data. And then you start building all of these aggregates, all of the different combinations that you might have, until you reach the apex of the cuboid, which is the summary, which is this one number that summarizes everything underneath it. Now, imagine this cuboid will get rather complicated as your dimensions grow in size, because as your dimensions increase, the permutations of these dimensions and the aggregates that you want to compute will grow in number. So if we have a 4-dimensional base cuboid, it means we're working with 4 dimensions. Then as you start building the different permutations, at 3D cuboids you already have 4 different aggregates that you need to compute. At the 2D cuboids you have already 6. At the 1D you go back to 4, and then you reach the apex, and that's all. So it has some kind of a diamond shape structure, where you start off with, well, the base cuboid, and then you reach this one level, but it might, as the number of dimensions increases, the middle tier, this middle area over here, will arbitrarily increase in size in a rather binomial fashion. So the assumption here with the cube model is that you build all of these aggregates. However, depending on the queries that you get, you might use all of these aggregates. So now that we've talked about the cubes, we've talked about the dimensions, and these are the central objects in the data warehouse, and we have them in store, what can we do with the data? And you have the basic operations that we've already seen before. So we can do a selection, so we want to select a certain part of the cube, we want only the sales in a certain city, so we only select according to a condition, which is the name of the city. We can have a projection, which basically means for the sales cube, I only want to look at a turnover measure. I'm not interested in any other measures. So you basically hold the same cardinality of the cube. It's the same size, but you're only looking at one measure. So in the different cells that you're getting, you're just cutting the cell, making it smaller. And you can join the cubes. And of course, you have all of these aggregation functions like averages, sums, and so on and so forth. So let's look at the first operation, which is the multi-dimensional selection. And the selection is usually you want to select according to a certain condition, according to a certain predicate. So you identify what you want to select according to this condition, predicate P, and in the end, you get all the cells, you get all these slices or small cubes that satisfy this predicate. So if you have the cube sales, you say you want all the measures that you have for this cube, and that satisfy that are basically videos. So in the product group, they are videos. They're not audio or something else. You only want the sales that are in your company for the video products. In the projection, unlike the selection, in the selection you only get might be only a certain slice in the cube, and you drop everything else in the cube, so you're only focusing on something. So in the selection, it could be, if we look at our cube here, And then we have the city over here, the time over here, and then the product. When we were looking at the video, that would probably be, we find the video here, for instance, and then since we wanted for all we didn't say anything about the time or the city, so we would probably want for all the different times, all the different days, months, years, and all the different cities. So that would probably be some kind of a slice over here. You can already see my 3D drawing is rather. So you return a slice of the cube. You don't get the entire cube, but rather you're zooming in on what satisfies your predicate, what satisfies the condition that you want. And of course, these conditions in the selection could be on all 3 dimensions. So we only had it on 1 dimension, which was the product dimension, but it could be more. And then as you select more, so if it was only on the time dimension, then probably you would cut off, and then you would have a smaller size over here because everything else here doesn't cut the condition that you have. In the projection, on the other hand, you always would return the entire cube, but since the cube in every cell cube, then what you do is basically, if you have different measures, you cut off this part, and then you have only 1 measure per cube, 1 measure in the cell. So here, the projection is basically you want only the turnover and the sold items on the sales cube. So had there been any other measures in the cube that you already identified when you were at the very beginning of the logical model, establishing the different cubes, entities, and the different measures that describe each of the facts, then you drop all of these. However, you get the entire cube, but only the different number of values within each cell with the cube is cut down to only focus on the measures that you want. So given a certain measure here, we're focusing on a certain measure on our cube C, we only get these cells that satisfy the condition. So we only look at, we're dealing with all of the different granularities, so we're including all of the dimensions, we're including the entire cube, we're not selecting anything, but we're focusing only on a certain measure, and we return only these cells only these measures within the cell that we're interested in. But the cardinality of the cube is the same. You get the entire cube. Another interesting operation that we can do is the join operation. So if you have different cubes, you can start combining these cubes together to get different values. So for instance here, if you have the sales and the price cube, by joining these cubes together and then calculating the unit price multiplied by the unit sold, then you can get the revenue. So joining the cubes together, sometimes you can get more insights or some values and numbers that you might need in your business. The only thing here when you're doing the joins is you have to be careful about something which is really important, otherwise the join operation doesn't make any sense. And this is rather intuitive. On the sales, you're working on the finest granularity that you have is day, while in the price, you're working on month. Joining these two cubes then doesn't make any sense, because joining a day to a month, what does that mean? It completely ruins anything that you're going to get at the end, if it doesn't even cause an error. So you have to be always careful about the join operation when you're joining. You have to have the same granularities, otherwise it doesn't work and you don't get anything that is meaningful. So if you have two cubes with granularity 1, the second cube with granularity 2, the granularities have to be the same. Once you have the same granularities, then you can start doing whatever operation that you want, which is basically the join operation. So how do you know whether the granularities are correct or not? So basically, at the very beginning, what we did is that we established the different granularities, and then we had these classification schema. And in the classification schema, you had all the different dimensions that you had, and you had a list of the different granularities. And since the different levels in the classification levels, they had these functional dependencies, they had these hierarchies. Once you look into the classification schema and looking at the different functional dependencies, you can understand whether a certain dimension has a finite granularity or not. And this could be done is, if you look at one dimension, and then at the finest granularity on this dimension, and you look at the other dimension, if there is a functional dependency on that, then this means if dimension 1 has a functional dependency on dimension 2, then this means that you could deduce the finest granularity in the second dimension from the first one. This means that the second dimension has a coarser granularity. It starts with the month. It starts with the product group, not with the article, not with the day, because you can deduce it from the finest granularity, from the first dimension. If there is a functional dependency, if it depends on a key value, then the dimension, the first dimension, has a finer granularity. So, given here, this is the mathematical term, if you have granularity G, and we're assuming this is the finer, so for instance, this could be the day, or this could be the article, and you have another dimension, and you want to test whether this indeed is, the first dimension has indeed a finer granularity, only if, so the second granularity is denoted here by the accents over here, only if there's a functional dependency, so if this second granularity is a function of the first, so the values are derived from here, or there depends on it, then you can establish that the first dimension was indeed a finer granularity. So if for every value in the second dimension it corresponds to another one in the first dimension, then it is a finer granularity. And the problem here is, well, what do you do now? You want to join the cubes together, and you have one dimension that is on the day level, and another dimension that is on the month level. Do you stop here, or can you do something? And what you can do is two solutions. The first thing, you can look in your classification schema and see if you have already a pre-aggregation. So if you had, in the first cube, the sales cube, you had day, month, quarter, and year. And the second dimension that you're joining in is on the month. Then you can easily roll up in the dimension, get the pre-aggregates for the month, and join on this level. If you don't have that, then you can compute the aggregate of the month on the fly, and then join the two cubes together. So you have to find some common ground, and that is always going in the dimension, in the cube that has the dimension with the finer granularity, and hop on to the higher, the coarser granularity, if it's there, if it's pre-aggregated. If not, then you compute it on the fly. So as an example here, we have two cubes that we want to join, the sales and the inventory. And as you can see here, in the time dimensions, the sales inventory starts with the day, while the inventory starts with the month. And here, as you can see, it looks like we already have the month. So what you do is, in the sales cube, you just hop on, roll up to the highest granularity, which is the month. It's already pre-aggregated, and then you work on that level, and you forget about the day. Had it not been there, and there was only day to quarter, then you compute it on the fly, and then you can do this join between the two cubes. The last operation that we can do on the cubes, and it's not only one operation per se, but that's a whole family of operations, is all of these aggregations. And these are similar to the aggregation functions that we had in relational databases. So this is everything from sum, averages, counts, But in the data warehouse, since things are more complicated, so in databases, when there is a function that is not there, we can, with SQL, code it ourselves and build it ourselves. But since we have this cube at the back end and things are a little bit more complicated, most of the packages that are out there will have everything that you can imagine in terms of functions, or means, medians, all the different functions that someone out there is using will be implemented, and you can directly use it, and you don't have to code something by yourself. An example here is the sum. So on the sales cube, you want to sum all the sales according to all the different product groups for different cities and for a certain month. So all of these aggregation functions are typically available for you. The functionality, the main functionality of the cubes is, this is where what is powerful about is using these aggregates. So the third topic that we were going to discuss with you today is this whole thing about supporting change in the logical model. So I've already told you at the very beginning how we've always been telling you that data warehouses are rather static, and you're probably ending up reading and not doing a lot of changes there. But rather, unlike databases where you do a lot of updates and inserts, it's once you load everything from the ETL, from that bulk point of time, then you typically do a lot of reads. However, things might change in your company, and you might have new requirements, you might have some queries that you didn't think of, and now you see that it is important for your company to investigate what's happening in a certain area, so something that you didn't perceive or think about in the requirement analysis phase. And you use average and to do that, you have to be able to change a little bit, tweak a little bit in the logical model that you already designed at one point to build the data warehouse. And again, you can have new requirements, or you can have also new data, new data sources, or new incoming products, or a new product line that you laptops, and then companies started selling tablets. Would you put these under laptops, or would you create a new category, which is tablets, and then put the data there? And if you already had the structure for the data warehouse, where do you put it? So you need to be able to modify a little bit the dimension, the classification hierarchy, to put this new category, the tablets, somewhere in there. You have to fit it in. And to do that, you have to be able to modify in your schema, in your models that you've already built before. So an example here is, it could be really any electronics store. So for instance, Saturn here. If we think about, zoom in about the mobile phone products, and let's say they've been holding the data ever since 2003. So we could imagine how classification hierarchy, how they would have built it. So having a top level which says, well, my product family here is the mobile, my product category is mobile. So back then, still no 4Gs. And then you have the different articles that are associated to each of these different product families. Now this worked fine until 2008, and then 2008, when all the 3Gs, the technology became affordable and everyone can afford it and start using it, everyone started wanting to have internet on their phones. The phone makers here, at, what they did is that for the O2 XDA, what they did is that it was the same product, however, they enabled the 3G on it. And now you had the same exact product, so it's not a new product to put it under 3G, but rather it's the same product, but it has a new capability now, which is it's now a 3G phone. And the question is now, what do we do? Do we keep it here, or do we add an edge here? According to the function dependency, each article has to be associated only with one product family. So you can't have two edges over here. It has to be one. If you delete this one over here, then what this means is that you've lost all the data that you've been holding before. This means that it was never a GSM article, and all the sales that you had for this phone before is non-existent anymore, when it should. You might want to, at one point, have a query that compares the sales of this particular phone when it was with the older technology and when it's now the newer technology, and compare which one fares better, which one is more likable, or how are the sales happening there? Was it a good move for the company or not? So this is a question, what to do here? Should you migrate it entirely to the 3G? Should you cut off this edge? What can you do? And one solution is to put it under 3Gs, but of course you lose all the information here. So it's something to think about. What can we do about this? But this is not the only problem, because you might be getting new products, so like the tablets, for instance, when I gave you the example at the beginning, or you have now the 4G phones with all the different phones like the iPhone 5 or the Samsung Galaxy S4, and in 2020 maybe we'll have the 5G phones. So there's always evolution, there's always the data evolves as your business grows, and you're always forced to somehow change a little bit in the data warehouse. So it's not static. You have to be able to flexibly do the changes so that it reflects your business operation. Otherwise, the data that you're storing is not out of date. I mean, it is out of date. It reflects the history, but then your history stops at a point which doesn't reflect your current business operation right now. And then all the analytical queries that you're doing would not serve the needs. Serve your needs for right now, because they're not, the data warehouse is not mapping to the actual reality of your company. So you have to modify a little bit the underlying schema. And now let's look at these two particular problems. What can we do? So if you have in this problem that we had, this issue when we had this article that's basically now falls under two product families, the GSM and the 3G. Well, the solution, we can borrow it from the file system, and this is what we've been doing all the time in the computer system, which is basically a versioning system. So you put some timestamps, and these validity timestamps tell you that up until 2008, this product was on the GSM product family. From 2008 and up, it's no longer in the GSM family, but rather now it falls under the 3G product family category. And by having these validity timestamps, when you have a query now, if you're only querying on older data up until 2008, or you want to only query about this article when it was with this phone when it was a GSM, then you run your queries up until the validity timestamp. So you basically would have some kind of matrix, and this matrix holds the different timestamps, and then you can see at which point in time was this article under which part of the hierarchy. And here, if you look at the point where we had the conflict here, then we say that this product was valid as a GSM product family from 2003, so from the very start when we started to save data in data warehouse up until 2008. And then from 2008 up until now, it's a 3G phone. And when you get a query, you direct it to the correct place. If you want to find out the total sales for this mobile phone regardless of whether it was a GSM or a 3G. Then you would have to break the query into two parts. At one point, at what part it would target this area over here, and then the other part of the query would run on this side, and then at the end you do a join, a union, and then you get the value for the entire query. So you basically break the query into two parts and then do a union at the end to get the correct value. And to find out about these timestamps, you would probably store it as a metadata matrix at the back end. And this can be easily visualized like that. So basically, on the columns, you have all the child nodes over here. And on the rows, you have the parent nodes. So if you look at the problem here, so the O2XTA, which is the child node of the product family GSM and 3G, you find that there are basically two entries here. So at one point, from 2003 up to 2008, it was a GSM product, and then starting 2008 up until now, it's a 3G product. And as soon as you have multiple entries for the same child node, then you know, okay, there is something here, you have to be careful, and the query has to somehow accommodate that. Now, of course, what might come to mind is how efficient is it to store these matrices, because as you can see, they're rather sparse, so you won't have a lot of sparse matrix. However, it's not really a problem because you don't have a lot of products. I mean, unless you're Amazon and you have millions of products, this solution works pretty well. If you're Amazon, then you probably have to do something else. But up until 100,000 articles, it's really not a problem to hold such a validity matrix with these timestamps. And the queries can run pretty fast and at a high performance level. Right. So what you gain from doing these timestamps is now your queries are rather flexible, because now you're retaining this information. You didn't cut off this edge here and say, I don't know anything about this article being a GSM product, I'm only caring about what's happening today, but rather you're keeping the data there and you're keeping it accessible, meaning that the queries can still access this data over here. And this gives rise to queries that are as is versus as was. So what was the situation as it is now, as a 3G product? And how is it faring as it was, so as it was in a GSM product? And you can do these nice comparison queries that gives you an idea of whether it was the right move or not. And this can only happen if you keep both edges in a way that doesn't contradict this functional dependency. So the two edges are not really there. Only one edge is available. Until 2008, this edge is over here available. From 2008 up until now, only one edge is there. So this was the first thing that we thought about. If there is some kind of a new article that just kind of like migrated, it's still the same, but migrated to another granularity in the dimension. But what about if you're introducing something that is completely new, or you want to delete a classification, one of the classification levels? What do you do then? And there's basically two solutions for that. You can either do a schema versioning, and what happens here is that you say, so in this example, for instance, you've realized that, well, I started off having, for the product dimension over here, at the very beginning, and when I was doing my analysis, I thought I would need 4 granularities. So I needed the article, the product group, product family, and product category. However, now that I'm running my business, I've noticed that, well, I'm not really getting a lot of queries on the product family. And you do care about that because you're dealing with huge amounts of data, which means computing this aggregate is rather expensive. So it's not something for you not to consider. It takes time in the ETL process. You're getting this data and you're aggregating that. And think back to the cube model. You're building all of these aggregates on top of the cube. And these aggregates have to be stored somewhere. And they take up space and they take up time. So, well, I don't use the product family anymore. Or I only get a few queries, maybe once a year or once every 5 years. Maybe then you can compute it on the fly rather than building it all the time, every time in the ETL process. And what you can do is, well, you just delete the product family altogether. And not a very clever idea in the sense that you're losing all of this data. You already had it before. And if you want to have a query that's incoming and wants to ask about the product family, you don't have that link anymore. You don't have that aggregate anymore. However, it's rather fast because you know that you're only working on one schema, so there's no validity stamps. You don't have to check which schema to use or what is valid now. You just have one schema, you go directly there. Product family is not there. Okay, I will compute it again. I'll do the aggregate. That is doable because you already have the product group, which is the finest granularity, and then from that you can build the product family, no problem. Had you deleted the article from here, that would have been a problem because then you wouldn't be able to compute it from the product group. The data is lost forever now, and you cannot get it anymore. But if it's something in the middle, well, then you can aggregate it again and recompute it. So the advantages for something like that is that, well, you have high flexibility. You query the product family for the old data, and you can always do and go back and aggregate it. The disadvantage is that, well, like I said, if the query comes at one point and the data is not there, you cannot go back in time and say, but I used to have it before, I had the data before. It's not there anymore. You've altered the schema and it's not accessible anymore. It's not there. So you would have longer query runtimes. But again, this is your decision. So if it's coming seldomly, it's not coming a lot, and weighing how much time you typically use to build this aggregate in comparisons to how often the query comes, it's a design decision. So it's up to you. However, if you do not like that solution, what you can always do is, rather than completely removing something from the schema, you can modify the schema, and then you can have different versions of the schema. So what you do is a simple modification to adapt the schema that you have now for the new requirements or what you want to do. So what you would have now is basically two schemas, the older one and the newer one. And then what you can do is, once you get a query, then you check which schema you need to query, either the older one or the newer one. Or if you want a query about the older one, which had the product family, you already had that data in there and you can get it instantly. On the newer schema, you don't have the data anymore, you can compute it. But now you don't have to compute the aggregate for the entire history of your data warehouse, but only for the newer part, only from the point in time when you actually modified the schema and the data was not there anymore. Right. So this was the logical model. Perhaps anyone has any questions? So we've talked about the cubes, the dimensions, and these were the central objects. And then we talked about how you can change a little bit in the logical model as soon as you have any changes in your business. The next thing would be the physical model. But maybe we can go to a break unless anyone have any questions. No? Okay, so we can meet again in 10 minutes. And like I said, the physical model, now we get to get our hands a little bit dirty and see how we can actually store the data on disk. And we start talking about the actual storage architecture. And this is where, let's say, the magic happens, because you have to be able to store the data in a way such that the queries, when they come, you can address them quickly, because the data warehouse holds, the amount of data is incredibly big. It's the history of your entire company, and on top of the history, you're building all of these aggregates. So we're talking about an incredible amount of data, and this has to be stored somehow. And since it's big, you will end up storing it on disk. And on disk, what you do is you store sequentially. And reading from the disk, as we all know, is expensive. And you have to carefully try and put the data together so that you don't end up going in and reading and getting a lot of blocks, because this takes a lot of time. And this is the question that we'll be answering now, is how we can store the data, organize it in a way such that when we want to access it, we access it in a fast manner. Of course, there are different strategies that can be used to fine-tune the performance, like indexing, partitioning, or materialization. We will not go into that this lecture, but rather the next lecture. Today, we will really focus on the actual storage architecture. And this is probably one of the first questions that, as a data warehouse architect or designer, this is the first question that comes to my mind: which model to use? Because there are different models, and in the last detour, I'll show you 4 of them. But there's 2 popular models to use. One is the multidimensional model, which is often also called the Kimball model. Or the relational model, which is also called the Inman model. And you've already heard about Inman, father of the data warehouse. So there are 2 different approaches, and we will talk extensively about both of them. And the obvious thing to do is the multidimensional model, because this is what the data warehouse is. When they first started thinking about data warehousing, this came rather obvious, that we're not talking about 2-dimension, but we're talking about multi-dimension, and we have to find some kind of storage that supports that. So at the very beginning, when people started implementing data warehouse, they failed drastically because they didn't have this underlying structure that can help them or boost their system to answer these analytical queries. Because the queries right now, they're rather complicated. They're not the quick, simple transactions that we used to carry out on a normal database, but they're rather complicated. They're trying to find some insights, so a lot of work has to be done. And when you're dealing with big amounts of data, you have to be careful how to store them. So the first thing that came to mind was this multidimensional model. But then came the relational database vendors, and they saw an opportunity for big money. They were already established in the market. They had all the relational database technology. It worked pretty well. Everyone knew them, all the big companies, and most of the companies had the technology already there. And they saw a chance, and they took it. And they basically said, well, what's the multidimensional data anyway? We have a table, and we can always somehow change it a little bit. We don't want to build something entirely new, so they were a little bit lazy there. They said, we already have our core relational database management system, and we can adapt it so that it supports the multidimensional model. And it worked pretty well, and they scored big time, and this is where Rollup came to be. So what they basically did is that they invented some special schemas, and somehow they adapted their technology. So we will see that in a few slides. But starting off with the multidimensional model. So we've already seen in the logical model, we're dealing with cubes. And since now we need to store the data on the disk, like I said, reading from the disk and writing from the disk is done sequentially. And we have to minimize that as much as possible. When you go to fetch some data, you better have them grouped together, better in the same block or in blocks that are close to each other. Otherwise, you're going to be spending a lot of time, because then you have to move across the different platters and then adjust the head and go and read the data, a lot of time. So the basic data structure that we would be talking about, since we're talking about a cube, then it's, at the end of the day, it's probably a matrix and arrays of some sort. And once you cut down this array and this matrix and you get these small arrays, then you can linearly put them on the disk. So the cube, like we said, it's a Cartesian product of the different dimensions that you have and the measures that is assessing the cube. And the idea is we want to store on disk, so somehow we need to linearize the data. And you have these multi-dimensional matrices, and for programming we know that matrices are basically an array of arrays. And now we just have to cleverly think of a way of how to put these arrays together side by side on the disk. And an example here, a simple example of a 2D cube. So we're only talking about 2 dimensions here. And basically we have here the product dimension. So we're selling pants, shirts, dresses, jackets, and coats. And over here we have the time dimension. And the time dimension we only have 4 months. So apparently we're a new company. And now whenever you have a query like what were the jackets that were sold in March, easily when you're looking at this matrix over here, well, I want to find the jackets that are sold. So here I'm looking at the jackets and March, and this is where I need to go and fetch the data from. Of course, if it's a higher dimension level, you can always look at the cube or the matrix and go and find the cell that you want. And now the idea is, how can we linearize something like this? And you basically have two choices. So the intuitive idea, you get one array, you put it on disk, and then you get the next one, and you add it over here, and basically you stick them together. Can anyone see what the problem with something like that could be once you do it like that? I mean, it's perfect. Now, for instance, once we start doing that, if I want to find everything, all the sales that I had in January, so let's assume that the disk, the block size is 5, so each cell here we have 5, and each block can hold 5 of these cells. And now I want the sales for January, so I go and I read this block, and I get the values. Seems good, right?
But the problem is when I want the data, for example, about all the jackets, then I have to jump from array to array to array.
Exactly. And these then are blocks. So these serves queries that are focusing on the time granularity pretty well. So all the sales in January, you can easily get them. For February, for March, very easy. But what about the jackets? The jackets, well, they're served in each of these blocks. So you have to jump from one block to the next. Every time you read a block, you get a value, go to the next block, fetch it from the disk, get it in memory, and then start adding all of these different values. Right, so this is a problem that instantly comes to mind, and we will look at it in a few slides. However, let's assume now that most of our queries are interested in the times. So I'm not going to be asking a lot of questions about the sales of my jackets over the entire year, but I'm always interested in how much did I sell from a certain product within a certain month. or how much in total did I sell over all the different products within a certain month. And how do you access that on disk? Because now they are linearly stored. So if I have the query here again, the jackets that were sold in March, here when I have the matrix, it's pretty easy to find. If you had the relational database as a table, that's also easy to find. Since now they're linearly stored on disk, we have to have some kind of mathematical function to find that. And that's also pretty intuitive. So now, finding the jackets that were sold in March, this means you have to jump 2 rows of the cardinality of the time dimension, which is 5. And then once you reach the third row in the time dimension, what you need to do is now to jump until you find the jacket. So you need to jump 1, 2, 3, and the 4th cell would hold the jackets. So given that the dimension 1, which is the time, is 5, so you already know the cardinality of each dimension. What you can easily do now is you have to jump the different dimension. You find out which dimensions you need to jump, and you jump with that cardinality, which is here 5, so you jump 10 rows, and then you identify in the product dimension at which point is that article in, which is basically 4, and then you jump until you reach the 4. So you jump the dimensions, and then you add up in the end the index of the item that you need to reach to. And this is rather easy to understand on the 2D cube, and this is why we gave here the 2D cube, but it also works on the higher dimensions. But in the higher dimensions, we're not talking about jumping 1 dimension, which is basically 1 row, which is now only, I'm jumping January and February, so I'm only multiplying 2 by the cardinality. If you go to higher dimensions, it gets a little bit complicated because you're not only talking about arrays, but you probably, if you're talking about 3D cubes, when you're jumping dimensions, then you'll probably be jumping a 2D plane. And after you jump the 2D plane, you have to jump the 1D dimension, which is now a row. And then after that, you can actually check the index of the cell that you need to reach and go for it. So this jumping of the dimensions always have to be multiplied by the cardinalities of all the dimensions. So you start off from the higher dimensions, the 4D dimension, you jump up to the 3D dimension, which is a cube, and then you jump to the 2D plane, and then you jump to the row. Once you're in the row, then you can start going according to the index until you reach your entire cell. And this is exactly what we did in the 2D dimension, but we only had 1 dimension that we were working in, so it was rather easy. We only had the 1 dimension, which is the row, and we just multiply by this cardinality. But it's exactly the same with the multi-dimension. We always multiply by the different cardinalities. So you start off here. The biggest dimension, all the cardinalities of the different dimensions, because you have to jump all of these dimensions, whether they are 3D or a 2D plane. And you go here, if it's a 3D plane, you're jumping to the 2D plane, and then from the 2D, you go to the 1 dimension, and then until you reach the row that you're in, and you just add this index to jump the cells, 1, 2, 3, 4. It's exactly what we did in the 2D dimension. Clear to everyone what we're doing here? Mm-hmm. All right. So now we come to the problem that we pointed out, which is our data on disk. It's highly influential on the performance of the incoming queries. Because like we said, for the queries of the jackets, if I'm more often getting questions about the products, then I'm losing big time, because then I am accessing the disk. For the jackets, for instance, if we're assuming that the block size is 5 pages, and each cell of here is so the 5 of them, each row is on an entire block, then getting the jackets query, which is how many jackets were sold in all of the years, you would have to read 1, 2, 3, 4. You would have to have 4 block accesses to get that. On the other hand, something like the date queries, how many jackets were sold in January, that is only in 1 block read. And you can see now, even though the complexity of the 2 queries is exactly the same, and you would expect that the runtime would also be the same, you're not getting the same results. You're getting, on one hand, the jacket query takes a lot of time. On the other hand, a query which is with the same complexity can be answered quickly. And this comes down to the queries that you have. So this is a decision that you need to do. You have to anticipate which types of queries you're going to get, so that the queries that will be often run on your system will be served quickly. Queries that will be seldomly run, well, then you can't have it all. So if you see that most of the queries are going to be like the jackets query, how many jackets, how many pants am I selling, then you would probably start saving it like this. So go the other way around. So it's a design decision. If you don't like that, and there is not one dominant type of query that is coming, but rather you do get both queries at the same time, you could always go and fall back to caching techniques. And caching techniques meaning you get the blocks and you cache it in memory. However, you have to be careful here, because this is what the operating systems also do. So you have to pay attention that the operating system is not swapping in or swapping out stuff while you're already caching the blocks in the cache, so that nothing is damaged. So if you take that into consideration and you're careful about that happening, then using some kind of a caching technique can help you with that. That was one problem that we pointed out in how the order in which, or how you choose to linearize your matrix or your cube on disk can influence the different performances of the different queries. This was one problem, but there are 2 other problems, and the 2 other problems stems more or less, you can say they're from the same family, and they have to do with how dense or sparse your cube is. So the cube, if they are dense, well, on one hand, this is very good and efficient in terms of storage, because then you're using your storage quite efficiently. On the other hand, your cubes are rather big, which means using caching techniques maybe will not be very efficient, because now getting slices from the cube in the memory is not good enough. The memory doesn't fit. And you have to manage this huge amount of data, and that's not very easy to do. You have to load it in memory, you have to work on it, and it might be tricky. A solution for that is, well, build an index on top of your cube, and then you would have 2 levels, and everything that you can do on the index, do it there. If you can do any joins, do the joins on the index. Whatever you can do in the index, do it on that higher level, because as soon as you go down to the data level, you're lost. The data in the data warehouse is very big, and you're dealing with highly dense cubes. So use clever indices on top, and use the indices to direct you to the places that you need to go to. And all the different operations, the basic operations that we've talked about, if you can do it on the index level, do it on the index level, and only then, after you've done everything you can on the index level, go to the data and fetch the data that you want. And of course, optimization procedures also that we'll talk about in the next lecture, like partitioning, or you could also always do some kind of compression and encoding. These we'll look at in the next lecture, but using a 2-level structure is rather a smart thing to do. A similar problem, relatively speaking, is having sparse cubes, and that's on the other side. Well, you don't have a lot of data. And the problem here is you have a lot of sparseness on empty cells, and you cannot really delete them, because you don't know. Maybe the data will come in at one point, and if you delete that, and you don't leave the space on the disk when you're putting the arrays, and you just delete that space, you cannot go back and say, oops, I have new data coming in, and I have to, on the disk, make space for it. That doesn't work. You have to then rewrite everything. Not a smart thing to do. So you have to keep the empty spaces. Another problem if you don't keep the empty spaces is, well, how do you know where to get to the blocks? We used a mathematical function before to compute it, and that was entirely based on the cardinalities and on counting where the data will be. That could be overcome, however, with using also an index on top. And once you use this two-level data structure, the index is rather like a map for you to know where to go. So it's like tracing pointers. The index points where the data is. That is if you choose not to store the empty blocks. Another solution for sparse cubes is to use two-level structures. So the index was one solution. The second solution is to organize your data on two levels. So you hold all the sparse data on the higher level and all the dense data on the lower level. So for example here, if you have a two-level cube storage here, which is the two-level structure, which is the solution. And you have the customer dimension and the product dimension, time, and geographical dimension. And these two dimensions, the marketing campaign and the customer, they have a lot of empty spaces in between. You don't have a lot of data. So you can kind of like separate them from the dense data. And this way you can address this part, use the indices, trace pointers, and you separate them from the dense data where you actually go and handle it in a different way. And this separation then makes things faster. You know where the sparse data is, where the dense data is, and where to use the different techniques. So this is another solution that you can use. This was Kimball's approach, which is the multidimensional model. The second model that you might choose to use is the relational model, which was a solution that and their goal was we already have the relational DBMS in place. We already have the kernel. The technology is there. Most of the people have it. And we don't want to change that. We want to keep what we have, just change a little bit, and get the big bucks in our pockets. So what they want to do is they want to be able to, of course, they're going to be dealing with multidimensional queries, so not the normal queries that you have. And they want to somehow be able to translate these queries that are incoming to the system. They translate it, and then this translated query would be a normal SQL query. Depends on the underlying database management system you're working with. And this query is translated, and then at the back end, it works on the relational database that they have. So they have to do this translation. Of course, the translation has to be efficient, has to be fast. You don't want to lose any semantic knowledge. And of course, maintaining the tables should be easy and fast. So the typical goals that you would want. So especially when you're loading new data from the ETL, from the staging area, this has to be also done efficiently. And when they start thinking about it, they have now tables in the relation database. That's that's the underlying structure that they're working with. And somehow now, what they want to do is they have this multi-dimensional structures, they have the cubes and dimensions, and they want to take it and somehow store it in these two-dimensional tables. And they said, okay, well, we can see the table could be seen as a cube. And how so? Well, we have in the tables the columns and the rows, and what we do is we take the dimensions and we put them in the columns, And then also the measures that you have also, they are placed in the columns. And then all the different cells that were in the cube, which were basically the measures for the facts, the turnover for the sales, or the unit price for the price cube. All of these measure values are then basically tuples in the table. And then we retain our relational database model. We have tables, and we have this huge table, and now we're holding all the data of the cube. Seems rather, let's take a look. Does it actually work or not? So now they have this incoming multidimensional cube, which has 3 dimensions: the product dimension, the time dimension, and the geography dimension. And now they want to convert this multidimensional cube data into the normal relational 2-dimensional table. And as you can see here, they start putting the article, which is the laptop. So here they start putting in the columns the different dimensions, and the 3 dimensions are there. And then they put so for both laptops and mobile phones, you start saying, okay, both of them are in Hannover, laptops, Braunschweig, Saturn, and what you can instantly see here now is the dimensions here. They're only article, store, and day. What about the higher aggregations? I mean, the cube wasn't only this, right? So this is the basic cube that they're working with. What about all of these different layers, the aggregate layers that we had on top? We had a lot of aggregates that were built here, and then at the very end we had this apex, which was all the aggregates, all the nice things that the cube offered us, the nice aggregates that you would instantly, with the query, as soon as you get it, you go get the aggregate, and that's it. Now when you have something like that, and you get one of these analytical queries, well, you have to do it, you have to run it. And we're only working here with one table, which is pretty big. They're not divided into multiple tables, but only one big table. And now, if you want to find all the articles, all the laptops, the sales of all the laptops that were sold in Hannover Saturn, then you have to go through the table and start doing that by yourself. So here's laptop in Hannover Saturn, mobile phones doesn't fit the bill, and then you start counting that. So these aggregates are not there. Where do you put them? Do you pre-compute it, and then when you pre-compute it, do you put it as a tuple here? So do you say, I have here article all and store Hannover Saturn, and for a certain, how do you do it? Is it a tuple? Is it a column? There's something semantically missing here. So doesn't really work well. They don't know how to handle these different classification hierarchies or the different dimension, or how to put these aggregates, which is the nice thing about data, about the multi-dimensional models, these different aggregates that we had. So this didn't really work out. So what they started thinking about is coming up with these different ways of representing the multidimensional paradigm, and clearly using one big table was not good. And the idea that they came up with is so-called snowflake schema. And they thought, okay, problem with the classification levels, we're going to create a separate table, and for every classification level, we were going to have a table. So we keep this big table, the fact table. It's not going to be as big as before. So in the fact table, we take all the columns that were for the dimensions. We keep the measures that we had before, and all the columns that were inside in the fact table. We take them out, and they are separate. They are a separate table. So for each classification level now, we have a table that has an ID, of course, And then it has all the attributes that are associated with this classification level. So for instance, for the time dimension, that could be the day, the month, the quarter, the year. And you can also have normalization for that. So if you look at the dimension of the time, you had something like this: month, quarter, and year. This was the time dimension. And you had also something like week here. And what they do now, they build a table for each one of those. And this could be done because it was a one-to-many relationship anyway. We had this functional dependency, which meant that one day is associated with 1 month, and then every month has many days. So the typical relational relation in the typical relationships in the relational database schemas, they break the time dimensions into these tables. And you basically have this one-to-one mapping of the classification hierarchies in these two-dimensional tables. And now, since we have this one-to-one mapping for the classification hierarchy, the fact table now doesn't need to hold these dimensions, but rather now the fact table holds only the measures, which was the revenue, for instance. And you need to connect, of course, the fact table with these dimensions. And so the fact table will have these foreign keys, which connects it to the different dimensions that we have. Why is it called a snowflake? It's called a snowflake because it looks like a snowflake. So you have this fact table in the middle, which was the cube, so the sales cube, and then you have the measures here, which is the turnover. And then you have foreign keys, and these foreign keys connect to the different dimensions that you have, which could be the time dimension over here, the product dimension, the location dimension, customer dimension, and so on and so forth. And it looks like a snowflake with the big important entity in the middle, the fact table with the measures, and it's connected to the different dimensions. An example here. So let's see. Over here we have the sales, which was our cube. And you have here the sales and the revenue. So we have two measures for this cube. And as you can see here, it is connected to 3 different dimensions. So over here, product. So you have the product dimension over here. And then you have store dimension over here. And over here, you have the time dimension. And for each of these classification levels, for each dimension, we create a table for each granularity. So in the product dimension, we start off with the finest granularity, the product, and then each product is associated with one product group. The product group may have many products, and so on and so forth. Product group with the product category. And what is interesting to note here is that in the fact table, you connect, of course, to the smallest granularity. So over here, you have a foreign key to the product ID, which is the finest granularity. You have in the time dimension a foreign ID to the day. And for the location dimension, you have it connected to the store ID, so to the finest granularity. And you start off with the finest granularity. And then when you get a query that needs, that is addressing, for instance, the product group, then what you need to do now is, well, you want to find out the sales of a certain product group. So you have to join with the product table and then join with the product group. So you have to do 2 joins. And this is not really very bad because now, since the dimensions are normalized, so these tables of the dimensions are rather small, because you're not holding all of the products information in one big table, and it's rather big, but rather it's normalized, so the different tables are small. So doing the joins is not very bad in terms of efficiency. And this is where the advantage of the snowflake comes from, is that once you start normalizing these dimensions, their sizes become small, and it's rather efficient in terms of the queries running faster. Of course, since you're normalizing, the question becomes, you're avoiding redundancy with that, of course, because you're doing the normalization, which was one of the major goals in the databases. Not really needed in a data warehouse because we're doing a lot of reads anyway, so we won't have a lot of updates. However, the idea here is that we want to run the queries fast. And as soon as you also start using a table for different granularities, then you can start to have queries on complicated dimensions, because if you have a really big complicated dimension with different granularities level, this breakdown of the different dimensions allow you to easily find out which table to go to, how the different joins should be done, and it doesn't matter to you if it is complicated or if it has a lot of different granularities. You can easily do that. It becomes rather problematic, though, if the fact table is big. Why is that? Because the joins between the dimensions is okay, because the dimensions are rather small, but the fact table typically is rather big, because the fact table is, at the end of the day, all the data that you want. It's the measures, and it's connected to every single dimension at its finest granularity. So you have a tuple for every sale, for every article, for every day, for every city. So it's connected on the finest granularity. And this means that the fact table is big, and joining then with the fact table is very time consuming. And this sometimes raises some concern. So this is one of the disadvantages of the snowflake schema. So it might pose a reduction in the performance of the overall data warehouse, because of these large intermediate tables that you get from the joins once you start joining with the fact table. So the star schema, and the star schema is pretty similar to the snowflake schema. So again, you still have this fact table in the middle, but now instead of normalizing the dimensions, you just put the time dimension in one big table. So you denormalize the dimensions, and the idea of that is that, well, you then start reducing these joins in the middle, and then you start to not have this as many of these intermediate tables that you get in the middle from the joins, and then this enhances the performance and makes things a little bit quicker. And you see the difference here from the snowflake schema is that you don't have anymore these different tables, this tail, the classification levels. You don't have then the different foreign keys, again on the finest granularity, which is the product ID or the time ID or the geographical ID. Of course, once you start doing this denormalization, the dimension tables gets rather big, and you introduce also a lot of redundancy, because every day in March, so 1 until 30, it will always have the same entry in the month, it will always have the same entry in the quarter, it will always have the same entry in the year. So denormalization introduces a lot of redundancy. This is not really problematic in the data warehouse in terms of data integrity, because you're mostly doing reads, you're not doing any updates. However, it takes some space, but you're also saving time on the joins, because then you don't have to do the joins between a different product group. And this comes down to the queries that are coming in. If you're getting most of the queries are coming on the top level, so most of the queries are coming on the year level, using a snowflake schema means you have to do one join with the time dimension, with the day, and then with the month, quarter, and then year. So 4 joins. If most of your queries are coming, however, on the finest granularity using a snowflake schema, it's good, because then you only need to do one join. You're joining only the sales with the first granularity, which is the day. So which schema to use, again, depends on what types of queries you're getting, and depends on your storage requirements, and yeah, mostly on the queries that you're getting. Advantages of the star schema is for often used data, the query performance is improved. So if you're getting a lot of queries on these higher granularities like the year or the product family, then it's easy because you don't have to do these joins. The data is there directly from one join. Of course, you're having smaller number of tables, so it's a rather clean design and the structure is simple. And you don't have all of these different dimension joins. So in terms of query processing, it's rather easier and faster and more efficient. But of course, you're introducing a lot of redundancy, which can be an overhead in terms of storage. And you're dealing with a lot of data, and you're going through a lot of data. And the question rises as to how to represent many-to-many relationships as well. Because what we had before was this one-to-many relationships, and this is easy to represent in one table. So for the day, you would have March, and then the year, but if you have a many-to-many relationships, in relational databases, a many-to relationships is basically represented with a table in the middle. But if you put everything in one table, how do you do that? That's a question with the star schema. If you want to have a comparison as a summary for the snowflake and the star schema. With the snowflake, the structure of the schema, it gives you, this, like I said, the one-to-one mapping. So you actually see the classification hierarchy that you had in the multi-dimensional model. Because each of these granularities in a dimension is represented by a table. You don't see that in the star schema because the entire dimension is represented in one table. In the snowflake, everything is normalized, so the dimensions, every single granularity has a dedicated table to itself, while in the star schema, you start to normalize the dimensions, so you don't have a separate table for each granularity or classification level, but you rather denormalize the dimension tables. An example here to see the difference in the back end in terms of the tables. In a snowflake schema, so we have here the product dimension, and as you see in the star schema, this is represented by one table. And then when you're looking for a certain article, you go to the article and then you have all the data over here. And you can see here that there's a lot of redundancy over here. On the other hand, in the snowflake, each of the different granularities is represented by the table. So the product here has a table by itself, the product group has another table, product category is another table. And once you have a query that wants to find the electronics article, then you have to start to do these joins. If we're looking at electronics here, then that would be, for instance, you're looking here at Nokia and Berry, and then using the foreign keys, you go over here, which is a mobile phone, and then electronics, and this is one of the electronics. Of course, there's also the Samsung and so on and so forth, but you might have here something that is clothes or something else, but you have to basically go with the foreign keys and do the joins, unlike the star schema. And the question is which schema to use, and there are some heuristics that might help you do the decision. So if you have a query, and the typical queries are always getting on the coarser granularity, like the product category or the year, then using a star schema is better. Then you don't have to do all the different joins. You don't have to do the 4 joins until you reach the last granularity that you have. If the dimension tables is rather small compared to the fact table, then also star schema is recommended. If modifications are rather rare, so you're not doing a lot of insertions, then it doesn't matter to you, this whole redundancy that we avoid with the snowflake schema anyway. So if you're doing mostly reads, which is typically what's done in a data warehouse, star schema is no problem, because you won't have any problems once you do modifications. And you have to do it everywhere? No, because it's mostly reads. So it depends. The question of which one to use is rather tricky. So there are some heuristics, but still not very clear. Both have advantages, both have disadvantages. And it comes down to fast query processing or efficient storage. And most people, what they do is that they don't choose one, but they use both of them. And it's a mixed form, and it's called a starflake schema. And the idea is, well, look at the dimensions that you have, and depending on the types of queries that are getting, some dimensions can be normalized, while others can be left to be denormalized. So for instance, if you're getting most of the queries on the time dimension on the year, then maybe you can denormalize the time dimension. Again, that is also, there can be a lot of talk on that, because if you're holding a lot of data over a long time, then the time dimension might be rather big as a dimension table, so maybe storage-wise, you might want to normalize that. So you see there's always this trade-off, and you always have to think about it. With the time dimension, it's a bit tricky. With other dimensions, it might be clear for you to see whether you would want to normalize it or denormalize it. Of course, you could always go back and change it if at one point you see that, okay, maybe I can denormalize that table. I'm getting most of the queries on the higher granularity. Again, there are some heuristics on which dimensions to normalize when you modifications. If you're having a lot, if you're changing a lot in the dimensions, then doing normalization is better, because then once you denormalize, you have to go over all the tuples and do the modifications everywhere. If you have a normalized setup, then you do the change in one place and it's reflected. That's not a problem for you. If the dimension elements are rather big, then normalizing is also better, because you're saving up a lot of space. If you have big dimensions and you choose to put it all in one table, then you're introducing even more overhead with more redundant data. So normalizing would be the way to go. Also, the same thing with the number of the classification levels. So if you have a lot of fine granularities within the dimension, then introducing this redundancy in the star schema might be also considered as an overhead. When thinking about the aggregates that we typically introduce in the multi-dimensional model to speed up the queries, if you're going to show that in the tables, probably also normalizing it would be better, so that you can quickly go and access it. So it gives you better response times. There are these were the 3 types of schemas. Basically, one was snowflake, starflake, and then there's the hybrid, which is what is often used. And this was only with one fact table. So you see one fact table, and we always had the dimensions surrounding that fact table. But of course, you might have different fact tables. And as you've seen at the beginning of the lecture, once you define a dimension, it can be used with not only one fact table, but multiple ones. And so if you have here 2 fact tables, 2 cubes, the sales and the receipts, and you can start joining the different fact tables to the same dimension. So the receipts could be connected to the product dimension, and the sales could be also connected to the product dimension. And then you have this big schema, and they basically call these the galaxy. So something like combining many star schemas together, and then you have this galaxy. Very creative with the names in data warehouse. Right, so we've talked about the multi-dimensional model and the relational model in details. Anyone have any questions in any of them? So these are the 2 popular models that at the very beginning you ask yourself which model to use, the multi-dimensional model or the relational model. There are more of them, so we'll go quickly over them. Both of these models, we've talked extensively about them, but we're going to have a different take, a different view on them now. There is the HOLAP, which is hybrid OLAP. It's basically an integration of both the multidimensional and the relational model, so it takes the best of the 2 worlds. And last one, which is called the desktop OLAP, it's rather a client-side solution where you can have something on your desktop, and then you can go around to your boss and show him, well, this is the cube over here, and these are the dimensions I have, and so it's kind of like a client-side processing, something that is small, light, so that you can run it on the desktop, and without not actually having a direct online connection to your data warehouse store. So the first model, which we already talked about, was the multi-dimensional OLAP model. And here what you basically have is, you have, of course, the presentation layer, which gives you this multi-dimensional view. And in the infrastructure, you directly have your multi-dimensional structure, so there's nothing in between. And all the pre-aggregations are already stored there. So you have the cube, and the pre-aggregates has been computed, and they're stored on top of the cube. And it's done in the loading step, so it's not done on the fly on the query. The aggregates are already computed and stored, so easy to access. Advantages, excellent performance. The aggregates are already there, so you just go and you get the values that you need. And we've seen this cuboid lattice at the beginning of the lecture, and you have here all the different aggregates. Of course, you can choose to save all of them. However, typically you don't do that for storage reasons, and even if storage is not a problem for you, you always have to think about, well, they take time, a lot of time for you to compute that and to prepare that. And it's not only a one-time thing at the very beginning, but rather the data warehouse always gets new data, and then these aggregates have to be continuously updated and continuously computed. So this has to be considered. Disadvantages of the multi-dimensional model is that there's a huge amount of overhead, because remember, we had this cube over here, and then on top of that we had all of these different aggregates that are built on top of the cube. And these aggregates, as you've seen, we have this diamond shape. And as the dimensions grow in size, this middle tier, also all these aggregates, all the permutations of the different dimensions also grow. And easily, with only having 10 dimensions, if you have a 200 megabyte file, it can easily go up to 5 gigabyte. And we're talking about data warehouse, you input file of 200 megabyte. You're not going to have that. It's going to be bigger. So it's an enormous overhead. And because of this huge amounts of data, you have these limitations of how you can handle the data. And that's typically why you have to have some clever indexing on top of that, so you can somehow have a handle for this data. So you do everything on the top level and then go to the data. with the multidimensional modeling, it's a completely different technology, unlike the relational one, which means you often have to buy a software that is already developed specifically to deal with this technology. Some of the products here are listed. You have the Cognos from IBM, you have Essbase from Oracle. There's also Palo, is open source and can be integrated also with the Excel sheet. This is for the MOLAP. The rollup is where we saw all of these different schemes, the star and the snowflake. This is where the relational database vendors said, well, we want also to get in on the train and, do something, and we can pitch in with our technology. And the advantages is, actually it works for them and it works for the companies, because all of the companies already have this underlying structure, this relational database management system. So you don't have to buy or invest a lot, because you already have the infrastructure there. As you can see now, unlike the MOLAP, you have something in the middle here, because you don't have the multidimensional server, the OLAP server directly, but rather here you need to have something intermediate, because you have to do this translation between the multidimensional queries so that it can be addressed by your relational database. So basically the presentation again gives you this multidimensional view. But at the back end, things are not done in this multi-dimensional fashion, but rather they go to the roll-up server, and here there is some kind of a translation, and then you get these SQL queries which the relational database management system can handle and can understand. And the schema designs that we've seen, like star or snowflake or starflake schema. And of course, since the data is kept in the database, and then you have this extra layer in between, and you have to do this translation, this takes extra time. So if you want to be, in terms of performance level, and to be as fast as the multidimensional model, which is pretty fast, you have the aggregates already stored there. So in the relational database, the aggregates are not there. You have to compute them. Then to reach that same level of performance, you have to employ some special indices like a bitmap or R-tree. So using indices is it's very critical to boost up the performance of a rollup model. Advantages, it's a proven technology, so everyone has been using it, everyone has it as an infrastructure already, so you need to do a lot of investments. It's not a new technology that you need to bring into the company. And it can handle large amounts of data, and that's not a problem. Disadvantages is you're limited to the SQL functionalities. With the multidimensional model, you had all the other different, you were working with the cubes, you had these nice aggregates here, everything has to be translated at the back end. You don't see it, but it's translated to SQL, and you're basically limited to that. There's a lot of products for that, like the MicroStrategy, Microsoft Analysis Service, or the Siebel Analytics from Oracle. So a lot of different solutions for that. If you want to compare both of rollup and MOLAP together, in terms of multidimensional view, so you always get this at the client end. You get the multidimensional view. You get these cubes. It's there. That's no problem. In terms of performance, MOLAP is better than rollup unless you employ some indices, and then you can get the same performance, because in the MOLAP the aggregates are all there already. In the rollup, an advantage is that you have a real-time data access, because you can actually go and fiddle around in the tables. In the MOLAP, the data is rather big, and getting very deep into these classification levels is pretty hard, and it takes time. Unlike the rollup, you have all these different schemas and they're normalized, and it's easy to drill down and go to the different granularities that you have. Other things is that, for instance, low aggregate maintenance with the MOLAP, you have low structure maintenance that needs to do with the rollups. Looking here easily, you can see that each of them has some pros and cons, and basically the idea is why not combine them together? So to get the best of both worlds, if you can afford it. And this is where the hybrid OLAP comes from. And the idea is you split the data between the two technologies. And there are two ways of splitting that, two alternatives. One is vertical partitioning, and the second one is horizontal partitioning. In the vertical partitioning, what you do is you have all of these nice aggregates that the multidimensional model gives you, the MOLAP gives you, and keep the aggregates in the multidimensional in the MOLAP, and this serves for the fast queries. While all the detailed data, so all the base cube, you can keep that then in the rollup. And basically, whenever you get the query, the aggregates can quickly be served from the MOLAP, and all the details then, which is the big data, you can't really handle it fast from the MOLAP. You can handle it from the relational model. A different alternative is you say, okay, on the MOLAP, which is faster, and all the older data, which maybe I'm not using it often, I'm not querying it very often, I'm going to put it on the rollup, and that's the bigger chunk of your data. So the smaller part of your data, which is the newer one, would be on the MOLAP, the multidimensional solution. The last solution, which is it's not really standalone, but rather you have to have something running at your back end, and then this is a desktop solution. And with this solution, you can run, you can have some of the data warehouse capabilities on your laptop, on your desktop, and you can have small hypercubes, so it's some more or less kind of like a presentation level. You can do multidimensional analysis, and you don't have to be connected to the data source, you don't have to be connected to the OLAP server that's holding your data, but rather computations can be done on the client side. And it's just a client-side solution, so little investments. Of course, you have to work with small cubes, so for heavy processing, this has to be done on the server. So you can't really manage large data sets. So it's just for the sake of getting some small amount of data and going to your boss or for the business analytics, and just to show them something. So it's a client-side solution. So this brings us to the end of the lecture today, and to the end of the data modeling phase. So last lecture we talked about the conceptual modeling. Today we talked about logical modeling, and we looked at the cubes, and we looked at dimensions, so all the central objects that we have, and we talked about the different granularities in each dimension. And then we moved on to the physical level, and we looked at how we can store the actual data, whether it's through a multidimensional model or a relational model. And in the multidimensional model, the basic structure was using arrays, and then we saw how we can linearize the arrays on the disk, because we have to access it sequentially. There were some problems with that, in the sense that the way you choose how to linearize your arrays affects the queries that are coming. Some queries with the same complexity will have huge varying response times. A solution for that was using caching, but you have to be careful about what the operating system is doing. And then we also had problems with the storage efficiency of the cubes, whether it's sparse or dense. And usually you have to build 2-level structures. You have to have either an index on the top and then do everything on the index level before you go into the data, or you can also divide the data, have this sparse level on the top layer and the dense one on the lower layer. And we took a quick look then into the hybrid OLAP and the desktop OLAP as well. In the relational model, we looked at different types of schema. So there was the star schema and the snowflake schema. And we did a lot of comparisons there. So star schema is good for the query performance. In the star schema, you denormalize the dimensions. In the snowflake, you reduce the size of the dimension tables by doing these normalization. Each table is mapped to single granularity or the classification level. And this, in terms of the physical model, like I said, you can still do a lot of fine-tuning for the performance. And this brings us to the topic of the next lecture, how to optimize that. And this is by using indices. This is by doing some partitioning. And we're going to be talking about, in particular, bitmap indices and tree-based indices next lecture. Any questions for today? Everyone happy? Okay, lunch break then. So, see you next time. Thank you for the attention.